we've been unable to get you some Computerphile listing paper today, but it'd be great if you could sort of show us some basics of how it works.
I will. This is going to be fun. So one of the kind of things we can do is, if a programmer wants to dispose all of the nodes in a tree, to delete them, they can write a recursive procedure that works like this. If I dispose the left subtree, and I can dispose the right subtree, then I end up with no tree. And so if I was to draw it, if I have a tree, then my recursive call would dispose this subtree, dispose this subtree, and then dispose the root node. So then free the root node. Now, there's a very interesting thing we can do. In this theory separation logic, we describe this very simply. We say the root node points to the left and the right. Mm-hmm. And separately, star, we've got a tree, which is the left, and a tree, which is the right. The star, this thing, is like normal logic, but it's and separately. It says it means there's no sharing between the two subtrees. Then what we can do is we can send the tree, left subtree here. Now I'm writing what Turing would have written as a program logic proof in 1949, but just using a funny symbols star, which is a bit different. And I can send the right subtree to this routine, and emp means I've removed all the nodes in the tree. And then after I remove all the nodes in the subtrees, I've still got this thing R. Let me call this root. See, this is what we end up doing on the blackboard. We end up rubbing things out and putting them back in. And then I just free this single node, and I've removed all the nodes in the tree. So this is a parallel way of removing all the nodes in the tree. And the way we work at it is we would tend to do this turns out that this is a mathematical proof in separation logic, a logical proof, that the routine that frees all the nodes in the tree, the parallel disposed tree routine, works like it's supposed to. So you see all the steps. You think of logic as being very complicated and very difficult maybe. All of the steps are very local and small, and they follow the intuitive reasoning which says remove this subtree, remove this subtree, remove the root. So you see, after we did a bunch of these by hand proofs, then we said, oh my God, this is working so regularly that perhaps we can make a computer do this. And so that's the kind of reasoning that the infer tool is doing on the tens of millions of lines of code at Facebook, is it's seeing the statements and it's pushing these formulae over the statements, but it's trying to keep the formulae as small as possible so it doesn't just blow up complexity-wise. So
in this instance, this might be those different kind of like paths down that tree might be the different possibilities the code has to follow. Is that right? And then
no, I've got the root of the tree, and I've got a left subtree and right subtree. I've just called them in parallel, because this is a challenging example for normal program verification, because if the left and the right subtrees happened to overlap, I would get a crash, or I'd get a data race at the very least. Okay. So in this case, they are different paths in the sense of different concurrent threads. So here's one concurrent thread, here's another concurrent thread. And so, in the C programming language, we might write this with pre-threads create before getting there. And I've written this using the parallel bar, which is something that people like Hoare and Dijkstra would have used in their programming languages before we ever had p-threads create. This is called structured concurrency. So when we mess about on the blackboard, we tend to use mathematical notation like this for parallel instead of p-threads create and join. But then when it comes to the tools that run in the real code, we have to convert this kind of mathematical reasoning into something that the C programming language or Java programming language can understand. But we can do that. We get at the essentials here in the Blackboard work, and then we translate that into something that the particular programming language can understand. This part will be described a little bit abstractly, but I'm going to show you what's called an inference rule in logic. So in something called separation logic or Hoare logic. So we usually say, we write things like this to say, if we execute the program where P holds beforehand, say there's a tree in memory, then we execute the program, then Q is true afterwards, where Q might say, the memory has all been deleted, or has all been given back to the allocator. Then there's a fundamental inference rule where this thing is called the frame. And this whole thing is called the frame rule of separation logic. What this says, if I do a mutation on a little bit of memory, then I can extend it to any bigger memory. So there's a principle of executing programs called in-place update. And so this locality of in-place update is like an operational truth about programs, but this brings it to a formal logical principle that covers many, many executions instead of just one at a given time. And it's this principle that is responsible for the scalability of our reasoning tools. So what we do is if a programmer submits a change to the code base, what we try to do is find the smallest possible p to describe the memory that change to the code base needs. Then we execute it to Q. And what we do along the way is for any little bit of program that needs a little bit of memory, when it needs to be put in a bigger context, we try to guess this. We use what's called abductive inference to try to guess this additional part R. So this, in essence, is a principle of locality. And so what happens is at any given time, there might be dozens or hundreds of changes to the Facebook code base. Our program analysis tool, for each of these, say, dozens of changes to the code base, a version of our tool is spun up in the data center, and it's running in the data center. And what it does is it looks at each of the little changes to all of the different changes that are going on at the same time, and it tries to guess, oh, this is just the little bit of memory that we need. Then we analyze that bit locally. And so we don't try to analyze the entire program. We just try to target the little changes and the little bits of memory they need. And so all of these analyses can go on and scale at the same time. The most important reason, there's a lot of things I'm not saying, the most important reason is that there's a principle of locality encoded here. That's quite an abstract explanation, but what I'm trying to convey is we're facing severe complexity problems. But if we can, my hypothesis has always been that the programmer reasons about code by looking at little bits of code at a time and looking at little bits of memory at a time, not all of the entire memory of the system. That's how the programmer works. So our mathematical theory is trying to codify that intuition of looking locally at the code. And then the tools try to take that mathematical theory, which codifies the local way of looking at the code, builds that into the theory. Then you get something remarkably which scales to tens of millions of lines of code. And if you didn't take this local approach, it would be very difficult to scale it. So that's quite abstract, but I thought it would be fun to give an inference rule for your audience.
I'm imagining all these data centers running obviously tens of millions of lines of code, but obviously running that in multiple instances, so there are potentially billions of lines of code running simultaneously. How many instances of infer are running then? Is it work like that?
Yeah. So at any given time, infer is so it's running once or twice continuously. It runs, then it runs, then it runs. But also, suppose 100 programmers. So Facebook has, I think, tens of thousands of programmers. Suppose at any given moment, say 100 programmers had submitted a change to the code base, then 100 instances of infer would be running. So at any given day, I think thousands of instances of infer run. And infer has a theorem prover inside of it, a theorem prover for guessing these, and for what's called abductive inference, which is, like I say, an old AI problem from the 1970s. It's a philosophy of science problem from earlier. There's thousands of instances of infer are spun up every day. And for each of the instances, the theorem prover is called many, many times. It could be hundreds of times, it could be thousands of times. So if you compare this to what I was doing as a scientist, as an academic, we would run one instance of our tool. And it would call the theorem prover 100 times. And then I was saying, oh my God, this is remarkable. We're calling a theorem prover 100 times and getting in answers. But then when I came to the company, then I found, oh my goodness, we're running it thousands and thousands and thousands of times per day, maybe millions. And to me, the scale is breathtaking. But the reason why it can work, once you understand, is this principle, with the principle of locality in your back pocket, it makes it possible, if it can scale to 1,000, maybe it can scale to 1,000,000 and to more. It's really quite remarkable. And I never would have predicted that I never thought about running these things, thousands of instances. I never thought about that.
Just thinking about the mechanism of it, are we running infer on a new piece of code to check it and then kind of like submitting it, or is it constantly checking things, or how does that sound?
So there's two modes. One is the constantly checking. That's for after the fact. But the way the software development process works is a programmer submits a code change. It's like a GitHub pull request. Then other humans make comments on that code change, and then if the code change is eventually accepted, then it gets committed to the code base. What infer does is it gets in at the code review time, so it's like a bot. So the other humans, the code reviewers, are making comments. Infer at the same time makes comments. So it might say, hey developer, there's a potential data race at line 43 here and line 55 there. There's a potential data race. Maybe you better look at it. It automatically writes a comment into the code review system. So in that sense, it's like a bot. But how it does that is when the developer submits the code change, at that moment, an instance of infer is spun up in the data center and it processes that code change. And if it finds anything, any potential issue, that's when it writes to the code review system, which is like a GitHub pull request. And then there are comments on pull requests. It would be like if our tool automatically wrote on the pull request. Now, so we had quite a bit of success with this, and it turned out that this mode of having the tool talk to the programmers during code review made it much more easy for the programmers to pay attention to the tool, to understand what the tool is saying, rather than the other way I would call it would be batch mode. Now, we're not the only ones doing this anymore. This is I think a movement, you might say, in the industry. There are startup companies that try to package tools like Infer, integrate them with GitHub, and then you have a way to work with GitHub. So there's Code Climate, I think, is one such company. Another company is MuseDev is a company that does this. So they're trying to integrate with code review, the static analysis tools.